The Mediterranean threw everything it had at the Judean coast that autumn morning in 22 BCE. Waves that had traveled unbroken from Cyprus hammered the shoreline, sending spray 50 feet into the air. No natural harbor existed here, no sheltering bay, no protective headland, just open sea meeting sand the way it had for 10,000 years. Inside a wooden supply shed, a Roman engineer named Marcus Severus watched 3 months of work disappear beneath the waves. The concrete pier his crew had built, standard formula, standard methods, everything done exactly the way Roman engineers had done it for generations, was breaking apart like wet bread. Chunks the size of ox carts tumbled into the churning water. The wooden forms they'd so carefully positioned were already gone, ripped away in the first hour of the storm. By sunset, nothing remained but rubble on the seafloor. Other engineers would have blamed the storm, bad luck, unusual weather, the gods expressing displeasure. Marcus had built on land for 15 years, aqueduct foundations in Gaul, temple platforms in Syria, warehouse walls along the Tiber. Solid, reliable work that still stands today. He knew what good concrete looked like, how it behaved, how it aged. But this was his first marine project, and something was fundamentally wrong. He'd followed every established procedure, burned limestone in kilns to make quicklime, hauled sand from the riverbed 2 miles inland, quarried aggregate from the hills east of the construction site, used seawater for mixing because fresh water was scarce along this coast. Standard formula. Every builder across the Roman Empire mixed it the same way, and it worked everywhere except in the sea. 3 more sections collapsed before winter. Each time Marcus adjusted something. Different sand, larger aggregate. Thicker walls. Each time the sea destroyed his work within weeks. This is the story of how a Roman engineer, working with a Greek consultant and an Italian ash merchant, discovered a concrete formula so effective that it would still be gaining strength 2,000 years later. But to understand why their solution worked, and why it took people willing to break every rule to find it, we need to understand just how brutally inadequate Roman marine concrete was, and how desperate the situation had become by 22 BCE. Rome ran on maritime trade. The numbers were staggering. Egypt alone shipped 150,000 tons of grain to Rome every year, enough to feed 200,000 people. Olive oil from Spain arrived in ceramic vessels by the millions, timber from Lebanon, marble from Greece, spices from the East, wine from every corner of the Mediterranean. The empire had conquered the known world, but that world was useless without ships to move its wealth and harbors to receive them. A single major port handled more cargo in a month than could travel overland in a year. The difference wasn't marginal. Sea transport cost perhaps 1/60th what land transport cost for the same weight over the same distance. An empire connected by sea was rich. An empire limited to roads was poor. Rome understood this, which is why Rome was desperate for harbors. But the Mediterranean coastline wasn't cooperative. Natural harbors, protected bays with deep water and calm anchorage, were rare. Most had been claimed by cities centuries earlier. The locations where Rome needed ports often had no natural protection at all. Open coastlines exposed to storms, shallow water that prevented large ships from approaching, seafloors of sand or mud that provided no foundation for construction. The solution was supposed to be concrete. Romans had perfected concrete construction on land. The Pantheon's dome, the largest unreinforced concrete dome ever built, still stands after 2,000 years. Roman aqueducts, bridges, and buildings demonstrated a mastery of the material that wouldn't be matched until the 19th century. Surely this expertise could be applied to harbor construction. It couldn't. Concrete that worked perfectly on land became worthless the moment it touched seawater. The chemistry was wrong. Though Roman engineers didn't think in terms of chemistry, they thought in terms of results, and the results were catastrophic. Standard Roman concrete used quicklime mixed with water. The calcium paste hardened as it dried, binding sand and aggregate into solid stone. On land, this process worked beautifully. The concrete set cured, and stayed cured for centuries. The chemical bonds that formed were stable and strong. In seawater, the process never completed. Salt penetrated the material constantly, dissolving calcium bonds before they could fully form. Waves pounded weakened surfaces, opening cracks that let more water in. Wet-dry cycles, as tides rose and fell, stressed the material from the inside. Structures meant to last generations crumbled within years, sometimes within months. The economic losses were enormous. A failed harbor project didn't just waste the construction costs, it wasted the years of planning, the political capital spent securing funding, the strategic opportunity of having a port in a particular location. Engineers who presided over failures found their careers destroyed. Some were exiled, a few were executed when their failures were interpreted as corruption or sabotage. By the 20s BCE, Roman marine construction had reached a crisis. The empire needed dozens of new harbors to support military operations, trade expansion, and administrative control of distant provinces. Engineers kept trying. Engineers kept failing. Some suggested abandoning concrete entirely for marine construction, return to cut stone, block by block, the way the Greeks and Egyptians had built. It worked, but a single harbor could take 20 years. The empire's expansion couldn't wait. That was the situation facing King Herod of Judea when he conceived his impossible project. Herod ruled as a Roman client king, which meant he held power only as long as Rome found him useful. He'd survived the civil wars that brought Augustus to power, switching allegiances at exactly the right moments. Now he needed to prove his value to the new regime. He needed to give Rome something it couldn't build for itself. The Judean coast had no natural harbor. Ships serving the region had to anchor offshore and transfer cargo to small boats, a slow and dangerous process that limited trade. A proper harbor would transform Judea from a provincial backwater into a major commercial hub. It would make Herod indispensable. The site he chose was a stretch of open coastline with nothing to recommend it except location. No protected bay, no rocky headland to anchor construction, no offshore islands to break the waves, just sand meeting sea. Engineers surveyed the site and delivered their assessment. Impossible. The breakwater would need to extend 200 meters into open water through depths of 30 feet or more. Waves during winter storms reached heights that would destroy any known construction. The seafloor was sand over bedrock, requiring massive foundations. Herod didn't care about impossible. He cared about impressive. He authorized unlimited spending and recruited engineers from across the empire. Marcus Severus arrived in 22 BCE with 30 workers and more resources than he'd ever commanded. Herod's money bought the best materials, the best equipment, the best everything. It couldn't buy knowledge that didn't exist. That first winter, after watching his fourth section crumble into the sea, Marcus did something unusual. Instead of immediately rebuilding, he stopped. He collected chunks of his failed concrete from the shallows where divers could retrieve them. He broke them apart and examined the pieces by lamplight, night after night, trying to understand what was happening inside the material. The exterior of each chunk looked solid, proper color, proper density, no obvious defects. But inside, the concrete was riddled with tiny channels, passages where water had penetrated and dissolved the calcium bonds. Some chunks were solid in the center, but soft at the edges. Others were soft throughout, like cheese that had been left out too long. The seawater hadn't just attacked the surface, it had invaded the entire structure.
Marcus tried changing his formula.
More quicklime, less quicklime, different ratios of sand to aggregate, volcanic ash, which some engineers swore improved concrete performance. Nothing helped for more than a few months. Reports reached him from other marine projects around the Mediterranean. A harbor extension in Puteoli on the Italian coast had collapsed after 2 years of construction. A breakwater in Antium, near Rome itself, was showing the same pattern of deterioration Marcus observed in his own work. Underwater foundations in Alexandria had failed despite the expertise of Egyptian engineers who'd been building in the Nile Delta for centuries. The empire's engineers were failing together, and none of them understood why. By year 2, Herod's patience was thinning. Pointed inquiries arrived from the palace. Requests for progress reports, reminders of the resources being consumed. Marcus understood the subtext. Produce results or be replaced. Replacement for an engineer who'd failed a king's prestige project wouldn't be gentle. He needed someone who understood not just that concrete failed in seawater, but why. Someone who had studied the problem across multiple sites and multiple decades. Someone who could see patterns invisible to engineers focused on their own individual projects. The name Demetrius came up in conversations with traders who moved between construction sites. Greek, from Rhodes, trained in the old traditions but experienced with Roman methods. He'd worked maintenance on the Pharos lighthouse at Alexandria, one of the 7 wonders, built 3 centuries earlier using techniques that Romans still couldn't replicate. Now in his 60s, Demetrius traveled as a consultant, examining structures, offering advice, collecting observations. Marcus sent a message. Demetrius was already in the region, working on one of Herod's palace projects. He arrived at the harbor site 3 weeks later. First impression, disappointing. Demetrius was old, slow, and seemed uninterested in Marcus's urgent problems. He spent 2 days walking the construction site without comment, picking up chunks of failed concrete, examining them briefly, setting them down. He watched the workers mix new batches. He studied the forms positioned in the shallows for the next pour. He asked questions about where the sand came from, where the limestone was quarried, where the volcanic ash was purchased. On the 3rd day, he finally examined Marcus's collection of failed samples. He picked up a broken chunk, turned it over in his weathered hands, and pointed at the channels inside. "See this? Salt water went through everything. Your concrete tries to keep water out, but the structures I've seen last longest, they don't keep water out. They take it in." Marcus waited. He'd heard plenty of theories from plenty of experts. Most were useless. Look at the strongest things in the sea. Coral, shellfish. They don't resist water. They build themselves from minerals in the water. They take what would destroy other things and make it part of their structure. This was philosophy, not engineering. Marcus needed solutions, not observations about shellfish. But Demetrius wasn't finished. He'd spent 30 years examining Mediterranean structures, and he'd noticed something strange. Most marine concretes degraded exactly as expected. Slow dissolution, gradual weakening, eventual collapse. Standard pattern. Predictable timeline. But a small percentage of structures didn't follow this pattern. They actually seemed to get stronger over time. Harbor sections in Puteoli that should have crumbled decades ago had grown more resistant instead. The oldest parts were stronger than the newest parts. This made no sense. Everything deteriorated with age. Everything weakened over time. Except these structures. Demetrius had examined samples from the strongest sections and compared them with samples from failed sections nearby. Same location. Same seawater. Same wave exposure. Different results. The only variable he could identify was the volcanic ash. Greeks in Alexandria used Egyptian ash. It failed. Engineers in Antium used Sicilian ash. It failed. Only structures built with true Puteoli ash survived. And not all Puteoli ash. Only certain types, from certain sources, mixed in certain ways. Marcus had used volcanic ash in his concrete, standard practice for 2 centuries. But he'd used whatever his suppliers provided. Ash was ash. A gray powder that made concrete cheaper and supposedly stronger? He'd never questioned its origin or quality. Demetrius explained his theory. Volcanic ash wasn't just filler. It wasn't just a cheap substitute for lime. The right ash, mixed with the right proportions of lime and seawater, might create entirely different chemistry. Instead of the seawater slowly dissolving calcium bonds, it might actually participate in forming them. The seawater might become part of the concrete itself. Might. Demetrius was careful with his language. He had observations, not explanations. He had patterns, not mechanisms. 30 years of watching structures, and he still couldn't explain why some survived and others didn't. But he had noticed something else. The strongest marine concrete wasn't just made with different ash. It was made with different methods. Standard practice mixed concrete cold, burned limestone in kilns. Let the quicklime cool completely, slake it with water to form a paste. Mix in sand, aggregate, volcanic ash, pour into forms. Wait for it to set. But some of the surviving structures showed signs of different preparation. Lime that had been mixed while still hot from the kiln. Volcanic ash added directly to reactive material. Heat during mixing. Not just before. Demetrius produced 2 small batches using the same ingredients. First batch, standard cold mixing. Second batch, ash added while lime was still hot. Both batches went into containers of seawater. Demetrius told Marcus to wait 3 months. The waiting was agony. Construction continued on other parts of the project, but the main breakwater remained stalled. Herod's messages became more frequent. Other engineers arrived to evaluate progress, their presence a clear threat. Marcus was running out of time. 3 months later, Demetrius returned to examine the samples. The difference was visible immediately. The cold mixed sample showed familiar deterioration, channels throughout, soft spots, crumbling edges, standard failure pattern. The hot mix sample was solid. Marcus picked it up, turned it over, squeezed it. Denser than when it was poured. No channels. No soft spots. 3 months in seawater, and it had improved. Demetrius pointed at the intact sample. When you mix hot, lime, and ash bond together before seawater arrives. They form something seawater can't break. Maybe something seawater makes stronger. But Demetrius couldn't tell Marcus exactly how to replicate this result at scale. He didn't know the optimal temperatures, proportions, or timing. He didn't know which volcanic ash worked best or why. He understood patterns from observation. He couldn't explain the underlying mechanisms. Find someone who knows ash the way I know stone. Someone whose family has been in the trade for generations. They'll know things that aren't written in any manual. The best volcanic ash came from the Bay of Naples, from the slopes of Vesuvius and the surrounding volcanic fields. Merchants there had been trading the material since before Rome existed, selecting and grading each batch with expertise, passed down through generations. Demetrius had heard of one operation in particular, a family business run by a woman named Lucia. Unusual for a woman to control a trading operation, but her father had died without sons, and she'd proven more capable than any male relative. Engineers who'd used her ash reported better results than those who bought from other suppliers. Whether this was the ash itself or her advice on how to use it, Demetrius didn't know.
Marcus took leave from the Caesarea project and booked passage on a grain ship returning to Italy.
1,200 miles across the Mediterranean, the same route hundreds of ships traveled every year carrying volcanic ash to construction projects across the empire. It was an absurd logistical operation, shipping sand halfway across the known world. But nothing else produced the same results. The voyage took 3 weeks. Marcus spent the time thinking about what he'd observed and what Demetrius had told him. Hot mixing, living ash versus dead ash. Seawater as participant rather than enemy. It contradicted everything he'd been taught, but everything he'd been taught had produced nothing but rubble. Puteoli was chaos when he arrived, one of Rome's busiest ports. Ships from every corner of the Mediterranean crowded the harbor, loading and unloading in a constant dance of commerce. Warehouses lined the waterfront, built, he noticed, from concrete that showed no sign of deterioration despite decades of exposure to salt spray and winter storms. He found Lucia's warehouse near the volcanic ash docks, in a district that smelled of sulfur and rang with the sound of loading crews. The building was modest, but the inventory inside was extensive. Dozens of ash varieties stored in separate containers, each labeled with codes Marcus couldn't interpret. Lucia was in her 40s, with calloused hands and a direct manner that cut through the polite indirection Marcus was accustomed to from Italian merchants. She evaluated him the moment he walked in, measuring him the way she measured her merchandise. "You want ash that doesn't die in seawater?" Not a question. She'd heard this request hundreds of times. Engineers arrived convinced they needed better volcanic ash. Most didn't understand what better meant. "What have you been using?"
Marcus described his suppliers in Caesarea.
Italian merchants who provided Puteoli volcanic ash at competitive prices. Lucia laughed. "They sold you funeral ash. Probably from the Alban Hills, mixed with clay and labeled Puteoli, because the name commands higher prices. That ash was dead before it left Italy. By the time it reached you, it was just expensive gray powder." She led him through her warehouse, pointing out different containers. To Marcus, the contents looked identical, gray to reddish powders of varying coarseness. To Lucia, each container held a distinct substance with specific properties and applications. Northern slopes of Vesuvius. Good calcium content, chemically stable, works well for land concrete. Worthless for marine work.
She moved to another container.
Vent near Pozzolana. Better chemical composition, but this batch has been stored too long. See how it's clumped? Moisture got in? Whatever made it reactive has already faded. Volcanic ash, she explained, wasn't stable material. Fresh ash was chemically active, full of compounds that wanted to react with lime and water and minerals. This reactivity was what made it valuable for concrete. But reactivity faded over time. Exposure to moisture accelerated the decline, Ash that had sat in a warehouse for a year or been shipped across the Mediterranean in leaky containers had lost most of its useful properties. Fresh ash wants to become stone. It's looking for something to react with. Old ash has already reacted with moisture in the air. It's finished. Dead? Mix it with lime forever and nothing will happen. She demonstrated. Small sample of ash from one container mixed with a pinch of lime and a few drops of seawater in a clay dish. The mixture warmed immediately, changed color, thickened into paste within minutes. Same test with ash from another container. Nothing. The powder sat inert, unchanged, uninterested in reacting with anything. Living ash and dead ash. They look the same. They feel the same, but one builds stone and one builds nothing. Lucia showed him the ash she'd recommend for his project. From the Campi Flegrei caldera west of Naples. Harvested 2 months earlier. Stored in sealed containers away from moisture. This ash is still waking up, still looking for something to react with. Give it lime and seawater and it'll form bonds that last forever.
Then she asked a question that surprised Marcus.
What water do you use for mixing? Seawater. Fresh water is scarce at Caesarea. Seawater is correct, but not because fresh water is scarce. This contradicted everything Marcus had been taught, every engineering manual, every experienced builder. Every piece of conventional wisdom said seawater was the enemy. You used it only when you had no alternative. It weakened concrete. It caused failure. Everyone knew this. Lucia shook her head. Everyone knows wrong. She explained what 3 generations of her family had observed. Concrete mixed with seawater and proper volcanic ash didn't just tolerate the marine environment, it thrived in it. The dissolved minerals in seawater, calcium, magnesium, sulfates, didn't attack the concrete. They participated in forming it. They combined with compounds in the volcanic ash to create crystalline structures that grew stronger over time. With dead ash, seawater destroys concrete, the calcium bonds can't form properly, and the salt dissolves what little structure exists. But with living ash, seawater becomes a building material. The concrete incorporates the minerals and uses them to strengthen itself. This was why her family had stayed in business for 3 generations while competitors failed. They didn't just sell ash. They understood ash. They understood that the material was alive in a chemical sense, that it needed to be handled properly, that the methods of mixing mattered as much as the materials themselves. Lucia provided specific instructions for Marcus's project. Ash no more than 6 months from harvest, stored dry, transported in sealed containers. High-quality lime burned from pure limestone without clay contamination. Hot mixing.
The lime should still be reactive when ash is added, generating heat during the combination.
The proportions were different from standard practice. 3 parts volcanic ash to 1 part lime for underwater work instead of the usual equal ratio. More reactive material meant more complete bonding, which meant better resistance to seawater penetration and speed. Once mixed, the concrete was actively reacting. Every minute of delay meant reactive compounds being used up before the material reached its final position. Every hour of waiting meant weaker final product. Mix, transport, pour, compress. One continuous motion. No breaks for lunch. No waiting for weather. No delays for anything. You're working with living material. Treat it like you're delivering a baby, not stacking bricks. Her ash cost 3 times what Marcus had been paying his previous suppliers. Payment in advance. No guarantees. If your workers don't follow the process exactly, my ash won't save you. I can give you living material. I can't make your people use it properly. The method is half the equation. As Marcus prepared to leave with his purchase, Lucia mentioned one more detail. The strongest marine concrete sheet examined used different aggregate than standard practice. Not the small gravel that was easy to work with and produced smooth surfaces. Large chunks of calcium-rich rock, fist-sized pieces, sometimes larger. Small aggregate is just filler. Large aggregate participates in the reaction. Seawater dissolves the surfaces of those chunks slowly, releasing calcium into the surrounding concrete for years. The concrete keeps building itself long after you've finished working on it. She'd seen harbor sections a century old where the concrete had grown around the aggregate chunks so completely that the boundary between rock and concrete had disappeared. The material had become one continuous substance, stronger than either component alone. Marcus made his purchase and arranged transport. The voyage back to Caesarea gave him 3 weeks to plan. New materials, new methods, new understanding, but also a project 2 years behind schedule and a king whose patience had limits. He would get one chance to prove the new approach worked. One test section. If it failed, his career was finished. If it succeeded, everything changed. Marcus arrived at Caesarea with his shipment of living ash and a completely revised construction plan. His workers gathered to hear the new procedures, and their expressions shifted from confusion to disbelief to open resistance. Hot mixing? They'd never done it. The reactive lime could cause serious burns. Working with hot material in the summer heat would be exhausting and dangerous. Deliberately using seawater. Everyone knew seawater weakened concrete. Every experienced builder had told them so. What Marcus was proposing contradicted generations of accumulated wisdom. Large aggregate that made pouring difficult. The chunks wouldn't flow smoothly into forms. They'd leave gaps and voids that would weaken the structure. Working with oversized material would slow production and increase labor costs. Rushed placement that exhausted everyone. No breaks, no delays. Continuous work from mixing to compression. In the Mediterranean heat, men would collapse. The senior workers threatened to quit. They'd signed on for a construction project, not an experiment that violated every principle they'd learned. Marcus was going to get people killed.
Marcus didn't argue. He didn't try to explain the chemistry or the logic or the observations that had led him to these methods.
He simply pointed at the rubble underwater, the remains of 2 years of conventional work. That's what proper procedures produced. That's what everyone knows how to build. We're trying something different. He offered bonuses for workers who stayed. Double pay for the test section. He promised to work alongside them, taking the same risks. And he chose the most challenging location for the test, a section of breakwater facing the full force of winter storms, completely exposed, exactly where conventional concrete had failed fastest. If the new approach worked there, it could work anywhere. The first step was producing quicklime. Standard procedure: load limestone into kilns, burn for several days until the calcium carbonate converted to calcium oxide, but instead of letting the quicklime cool in piles while workers prepared other materials, Marcus had them move still hot lime directly to the mixing area. The heat was intense. Workers wrapped their hands and kept water nearby for burns. The volcanic ash went into wooden troughs, and hot lime was added directly on top. The reaction was immediate and visible. Heat radiated from the mixture as the calcium oxide began bonding with aluminum and silicon compounds in the ash. The color changed, steam rose. Workers stirred the mixture with long wooden paddles, keeping their faces back from the fumes. Gradually, seawater was added, not enough to make the mixture soupy, just enough to create a workable paste. The proportions had to be precise. Too wet, and the reactions were diluted. Too dry, and the material wouldn't fill the forms properly. Large aggregate chunks went in last, pieces of limestone and tuff cut larger than any of the workers had used before. Some pieces were the size of a man's fist. Others were larger. The workers complained that the mixture was impossible to work with, that it wouldn't flow, that they couldn't fill the forms properly. Marcus insisted, "Pack it tighter. Compress it harder. Force it into position." The mixed concrete went into baskets and onto waiting boats immediately. No staging, no delays. Workers rowed to the construction site and dumped material into wooden forms that had been positioned underwater. Other workers standing on platforms used long poles to compress and settle the concrete, forcing out air pockets, ensuring contact with the forms 6 hours straight. No breaks. Mixing, loading, rowing, pouring, compressing, rowing back for more. Men rotated through positions to prevent exhaustion, but the pace was brutal. By sunset, they'd placed a section roughly 10 meters long and 3 meters wide. Not much compared to the overall project, but enough to test whether the new methods worked.
Marcus examined the surface as the sun went down.
Already harder than previous attempts at the same stage. The color was different too. Less gray, more uniform, with a slight warmth that suggested ongoing chemical activity inside. Then winter arrived, and the waiting began. Storms battered the coast for months. Waves that had destroyed every previous section hammered the test area with mindless persistence. Marcus watched from shore, unable to do anything but observe and hope. Some nights he couldn't watch. He'd lie in his quarters listening to the wind and the waves and imagine the concrete crumbling, another failure, his career finished, his methods proven wrong. But each morning when he walked to the shoreline to survey the damage, the test section was still there. Waves broke against it and fell back. The surface was scoured and smoothed by constant water action, but no chunks broke away. No cracks appeared. The concrete simply sat there, taking everything the Mediterranean could throw at it. After 3 months, Marcus arranged a diving inspection. A worker with salvage experience swam down to examine the base and underwater surfaces, the areas most vulnerable to seawater attack, the places where conventional concrete always failed first. The man was underwater for a long time. When he surfaced, his expression was strange. "It's solid. All of it. And he struggled to find words. It's attached to the seafloor, like it grew there, like it's part of the rock underneath." The test section hadn't just survived. It had bonded with its environment. The concrete had merged with the seafloor beneath, filling gaps between rocks, conforming to irregularities in the bottom. The boundary between construction and natural stone had blurred. Marcus expanded production immediately. More ash ordered from Lucia, shipped in sealed containers to preserve its reactivity. More workers trained in hot mix methods, more sections poured following the same demanding process. The results were consistent. Section after section held. Month after month, the breakwater grew outward from shore, extending further into the Mediterranean. Workers who had threatened to quit became advocates for the new methods. They could see the results in front of them. Other engineers on the project remained skeptical. The hot mix process was dangerous. Several workers had suffered burns despite precautions. The fresh ash requirements were expensive, adding shipping costs that multiplied the overall budget. The rushed placement schedule was exhausting, limiting how much could be accomplished each day. One senior engineer, a Roman who'd built harbors in Italy, told Marcus he was overcomplicating things. Concrete was concrete. You mixed it and poured it, and it either worked or it didn't. All these special procedures were unnecessary mysticism. Marcus invited him to dive on the test section. The man went down skeptically and came back up with a different expression. It's solid. Solid like bedrock. Solid like it's been there 1,000 years. News spread through the network of Roman engineers. Marine concrete that actually worked. That survived winter storms without damage. That seemed to grow stronger instead of weaker over time.
Engineers from other projects made the journey to Caesarea to see for themselves.
They dove on the structures, examined samples, interviewed workers. Marcus shared everything. Ash specifications, hot mix procedures, placement timing, aggregate selection. He had nothing to gain from secrecy. The empire needed harbors. More importantly, he wanted the knowledge to spread, to be tested by others, to be refined and improved by engineers facing different conditions in different locations. By 15 BCE, 7 years after Marcus arrived, Caesarea Maritima was functional. Massive concrete breakwaters sheltered an inner basin large enough for hundreds of ships. Underwater foundations supported warehouses and loading facilities. Concrete moles extended into the sea, creating protected channels for vessel traffic. Ships from across the empire docked at a location where no harbor had ever existed, where no harbor should have been possible. The concrete held. Herod got his magnificent port. Rome got a major commercial hub on the eastern Mediterranean. Marcus got a reputation as the engineer who'd solved marine concrete. But the solution wasn't his alone. Demetrius had provided the observational framework, the recognition that some concrete survived while most failed, and the identification of hot mixing as a critical variable. Lucia had provided the material science, the understanding of living versus dead ash, the importance of freshness and source, the role of seawater as participant rather than enemy.
Marcus had integrated their knowledge with practical construction experience and proven the combination at scale.
The collaboration mattered. No single person understood enough to solve the problem alone. It took a Greek who watched structures, an Italian who knew materials, and a Roman who built things. 3 different kinds of expertise combined. Marcus stayed at Caesarea for 5 more years after the harbor opened, training local engineers in the new methods. He wanted the knowledge embedded in regional practice, passed from experienced workers to newcomers, not dependent on his presence or written manuals that might be miscopied or misunderstood. He documented his procedures anyway, and those notes eventually found their way into construction manuals that circulated throughout the empire. The specifications became standard for marine work: fresh volcanic ash from Puteoli sources, hot mixing, seawater incorporation, large calcium-rich aggregate. Engineers carried the techniques to new projects across the Mediterranean and beyond. Harbor expansions in Alexandria, breakwaters in Carthage and Leptis Magna. Underwater bridge foundations across rivers that had resisted Roman construction for decades. Fish ponds along the Italian coast. Cisterns that had to hold seawater for live fish markets. Anywhere concrete met salt water, the new methods spread. Within a generation, Roman marine concrete had transformed from constant failure to reliable technology. Harbors that would have been impossible became routine construction projects. The empire's commercial network expanded accordingly, connecting regions that had been isolated, enabling trade that had been impractical. The formula outlasted Rome itself. When the empire fell, the knowledge scattered with it. Medieval builders knew Roman harbors lasted. They could see the evidence in front of them, but they couldn't replicate the results. The specific requirements were too demanding. fresh volcanic ash from specific sources. Hot mixing that required careful temperature control, rapid placement that demanded organized labor crews. These weren't things a medieval mason could improvise. The techniques were forgotten. The structures remained. Fishermen moored their boats to Roman breakwaters. Merchants built warehouses on Roman foundations. Coastal villages grew around Roman harbors because the concrete was still there, still solid, still functional after 1,500 years.
Modern engineers rediscovered Roman marine concrete in the 20th century, first as a curiosity and then as a challenge.
How had ancient builders produced material that outperformed modern Portland cement? What did they know that we had forgotten? The answers came slowly. Through careful analysis of samples from ancient harbors, through chemical testing and microscopic examination, the volcanic ash contained compounds that reacted with seawater to form crystalline structures, aluminum tobermorite and philipsite, that grew denser and stronger over time. The hot mixing created lime clasts, pockets of calcium that slowly released minerals into surrounding material, continuously reinforcing the structure for centuries after construction. The concrete wasn't just durable. It was self-improving. It used the very substance that destroyed ordinary concrete, seawater, as a building material. It converted enemy into ally through chemistry that Roman engineers didn't understand, but had learned to harness through observation and experiment.
Marcus died around 30 CE in his late 70s, long enough to see his methods become standard practice throughout the empire.
He never knew why his concrete worked at the chemical level.
He knew that it did work, that following specific procedures with specific materials produced specific results. That knowledge was enough. It had to be enough because the underlying science wouldn't exist for another 2,000 years. Roman engineers built by observation, by trial and error, by paying attention to results and adjusting methods accordingly. They didn't need to understand crystallography or mineral formation. They needed to know which ash to buy, how hot to mix, how fast to pour. Sometimes that's how discovery works, not through theoretical understanding, but through practical observation. Someone notices that certain conditions produce certain outcomes. Someone else figures out how to replicate those conditions reliably. The explanation comes later, or doesn't come at all. The explanation for Roman concrete came in the 21st century. The concrete itself had been working for 2 millennia by then, indifferent to whether anyone understood it. Divers touch it today, 2,000 years after Roman workers compressed it into place. The harbor at Caesarea is gone. Trade routes shifted, the coastline changed. Sediment buried everything above water. Earthquakes toppled what sediment didn't cover, but underwater, in the darkness, the breakwater remains. The concrete Marcus built, using methods he learned from Demetrius and Lucia, still sits on the seafloor. Still solid, still bonded to the rock beneath, still getting stronger.